We spend a lot of time thinking about the flashy tech in our lives. Our phones, our smartwatches, all that stuff. But what about the really important tech? The powerful, hidden engines working silently, right beneath our feet, doing a job so fundamental we just completely take it for granted. Well, today, we're going to dive deep and uncover one of those unsung heroes. So let's start with this number, 97.5%. What is that? Well, that's the percentage of all the water on planet Earth that's saltwater. That's right. Almost all of the water on this blue planet is totally undrinkable for us. Which, of course, leads to the big question, right? If we're surrounded by water we can't use, where in the world does the fresh, clean water that fills our glasses and grows our food, where does it actually come from? To figure that out, we're going to go on a little journey here. First, we'll tackle the hidden water challenge. Then, we'll meet the unsung hero that solves it. We're going to look at the dangers of getting it wrong, see how this tech survives in insane conditions, and then finally, we'll connect all of it back to you, turning on your faucet. All right, let's kick things off with part 1, the hidden water challenge. It's time to get a real sense of just how limited our freshwater supply truly is. Okay, so this chart really puts it all into perspective. We already know 97.5% is salt. That leaves this tiny sliver, just 2.5% as freshwater. But here's the kicker. 2/3 of that is frozen solid in glaciers and ice caps. When you do the math, it's pretty staggering. All of humanity, our cities, our farms, everything, we rely on less than 1% of all the water on Earth. And we get that tiny fraction of water from two main places. You've got surface water, rivers, lakes. It's easy to see, but it's also exposed to all sorts of stuff, so it needs a lot of treatment. And then you have groundwater. This is the good stuff, hidden away in underground aquifers. As it trickles down through layers of rock and sand, it gets naturally filtered. It's often incredibly high quality from the get-go. And this is where engineers get really clever, combining the best of both worlds. It's called riverbank filtration. Instead of just sucking water right out of a river, you drill wells right next to it. By doing that, the ground itself becomes this huge natural pre-filter. We're talking about removing something like 90% of bacteria and other nasty stuff before we even have to start treating it. It's just a brilliant piece of engineering. But here's the problem. How do you actually get that water, whether it's from a deep aquifer or one of these riverbank wells, all the way up to the surface? Well, that brings us to section 2, where we meet the unsung hero of this entire story. See, whatever solution we use, it can't just sit in some nice, clean factory. It has to be lowered, sometimes hundreds of feet down into the dark, into a narrow pipe, and it has to work perfectly, completely submerged, for years on end. And this is it. Meet the submersible pump. Now, this isn't just a motor with a fan on it. It's a completely integrated, super powerful unit. The motor is hermetically sealed, the pump is incredibly efficient, and the whole thing is designed from the ground up to spend its entire working life underwater. I mean, at its heart, its job sounds simple, right? Just push water up. But really think about what that means. This machine is fighting gravity, hour after hour, day after day, to push thousands of gallons of water from way down in the earth all the way up to where we can use it. It's pretty amazing. But, just having a powerful tool isn't the whole story. How you use it is absolutely critical. And that brings us to section 3, the dangers of pumping. Because if you get this wrong, things can go south fast. This is probably the best analogy I've ever heard for it. Overpumping is like drinking a milkshake so fast you collapse the straw. We've all done it, right? You suck too hard on a thick milkshake, create too much vacuum, and the straw just caves in. Well, a shockingly similar thing can happen to a water well. So this chart kind of shows what's going on visually. When you turn the pump on, the water level around it drops. That's called the drawdown. Now, if you're in the green zone, the flow is nice and sustainable. The water level drops a bit and then stays stable. But if you get greedy and push it into the red zone, the water level plummets. You're basically pulling water out way faster than the aquifer can naturally refill it. It really is a Goldilocks problem. You've got to find that just right flow. Do it right, and you have a system that can last for decades. But overpumping? Man, you risk collapsing the well, sucking in sand and contaminants that clog and destroy the pump. It's not just bad for the equipment, it's a huge waste of energy and money. Now, as you can imagine, these pumps don't always get to work in nice, clean drinking water wells. They get thrown into some of the most brutal environments you can think of. So let's jump to section 4, surviving extreme conditions. And I mean, we are really pushing the limits here. These things are used to pump acidic water out of mines deep underground. They're made of special alloys to handle super corrosive salt water. They're even laid on their sides, horizontally, to move water around in reservoirs or power fountains. They even have to be able to handle water that's full of dissolved gas. In these tough spots, engineers face this terrifying enemy called cavitation. Here's what happens. If the pressure inside the pump drops too low, the water literally boils, even if it's cold, forming tiny vapor bubbles. As those bubbles move into a higher pressure zone, a split second later, they collapse with incredible violence. Seriously, just think of it as the pump being attacked by thousands of tiny, non-stop underwater explosions. And this performance curve shows you exactly what happens. A healthy pump runs along that smooth upper curve. But the second cavitation begins, performance doesn't just dip a little, it falls off a cliff. Those tiny explosions are physically blasting away bits of metal from the inside of the pump, literally tearing it apart from the inside out. Okay, so let's bring this all home in our final section, engineering on tap. We've seen the huge challenge, we've met the technology, and we've seen the dangers. So what does it all really mean? Let's just quickly recap the incredible journey that water takes. First, we have to access that hidden groundwater, sometimes miles deep. Then it has to be pumped at that perfectly balanced, just right rate. Along the way, it has to survive brutal conditions, fighting off things like corrosion and those tiny explosions of cavitation. And only then, after all of that, does it show up as a clean, reliable stream of water at your tap. It's pretty wild when you stop and think about it. The final result of all this mind-bending engineering, all this fluid dynamics and material science, is something we don't even think twice about. It's just the simple, reliable flow of water, the very thing that makes our homes, our farms, and our cities possible. So I'll leave you with this question. The next time you turn on the faucet, maybe to get a glass of water, will you take just a half second to think about that unseen engine, that silent hero working away hundreds of feet below the ground, just to push the planet's most precious resource right to your fingertips?